Thanks a lot. And indeed, I want to switch a bit back from more maths-related topics to more chemistry-related topics. And in doing so, I actually want to stand still a moment at the topic of this workshop, which is actually stochasticity in electrochemical modeling. So where do we actually meet stochasticity? And I think this is really very broad where we have that, and I think we have seen several examples already. But some of them have actually so far gone unnoticed, so I want to just summarize a few more. And I think very importantly, what we have not at all seen yet is that the electrode structure is changing under electrochemical conditions. So we could consider this stochastic, because every time you do this again, you'll end up with a slightly different electrode. So there's a lot of stochasticity in the exact structure of our electrodes. Then on this we have heard already, the water structure, it will change dynamically, so at every moment in time it's a stochastic process. And the same holds true for the ion arrangement. And I think here the beauty is that sometimes we can get around this stochasticity by simply describing mean effects, and we often hope to get around that by describing mean effects. We discussed a bit about potential fluctuations that should happen on atomistic scales or field fluctuations. And another one that I think we've slightly touched upon is mass transport. And we have touched upon ideal mass transport, but what we haven't heard at all yet is bubble formation. And that's actually another point that is important in electrochemical situations. And for example, in electrolyzers is really an important part to take into account while designing such a thing. Now, I myself, I'm actually working currently mainly on these two effects here, and I think that is where we fit very well to what is going on at this workshop in general. So that kind of brings me to my title, the double layer properties at the atomic scale. So what is the double layer? Maybe for the mathematicians, the double layer is what we call the structure that arises at a typically charged interface. So you have some interface, you charge it, you have an electrolyte next to it. This electrolyte will somehow arrange, the dipoles in the water will arrange, but also the ions will react. And this entire structure from the charged interface all the way until we have reached kind of bulk properties, we call the double layer. And it's really, for me, it's a lot about kind of getting this atomic scale insight. And I'll explain in a second why. So what I want to do with my research very often is to see what we can't see, and with that I mean what we can't see in experiment. So you have an experiment that tells you a lot. I love to collaborate with experimentalists. I think it's very important. But there are some things that are hard to see in experiment. And I think out of the collaboration between theory and experiment, very often we can actually really see the things that we can't see. And importantly, what I always hope to find is some concepts that are so simple that we can distill them into a more generalizable thing, such that when the next person does their experiments, they can come with ideas, oh, this could be due to A, B, and C, and have an argument of why this could play a role. Now, one of the most known and maybe the oldest concepts that we actually have in electrochemistry is the Guy-Chapman-Stern model about this kind of double layer. So what this Guy-Chapman-Stern model essentially says is that we can predict the average positions of ions based on a simple concept. You have an electrostatic pulling force for the counter ions towards the surface. But as ions don't particularly like to have density gradients, you also have an entropic push. And the two of them at some point will be in equilibrium, in which case you find your equilibrium structure. Also, the ions cannot bang into the surface. That gives you this additional Stern term. And through this equilibrium, what we essentially find is some kind of average distance of the ions from the surface that will give rise to what we call the double layer capacitance. So you can really think of this very simplistically speaking. You have your ions here in one layer, you have the counter charges in another layer. This already looks a bit like a capacitance, right? It's not quite that easy, which also means that this capacitance will depend on the potential, but the concept remains exactly the same. So we have this double layer capacitance, and what Guy Chapman-Stern now actually predicts is that we have at potentials far away from where this surface is uncharged, the capacitance will be dominated by what we call the Stern part, or the Helmholtz capacitance. And as we go towards the potential of zero charge, when this electrostatic pull force is small, if we go to very low concentrations where the entropic kind of push is very big, then on average the ions will be very far away from the interface, and you will end up with a very low concentration. So that's a very nice concept, and it has been used all over the place. And I don't want to say that this is useless, but what I do want to say is that it often does not quite work out. So this is an example of platinum 111. At low concentrations, at very, very low concentrations, actually, we do find this minimum, but the minimum does not scale in the way we expect from Guy Chapman-Stern theory. And at higher concentrations, we find a bump, which also Guy Chapman-Stern would not exactly predict. So clearly, this does not meet our expectations, so something is missing in the model. And this something will have to do with something on the atomistic scale. So that might be an ion attraction, something about OHs, water maybe adsorbing or desorbing, water reorientating in a way that we do not expect. So all these effects could play a role, and in fact, we can now go and make a toy model in which we add some ion attraction, and we play with the parameters of how strong this ion attraction is, and ta-da, we can actually find values here that would match the experiment. So this is, I'm plotting 1 over the capacitance and 1 over the expected capacitance from this Guy Chapman-Stern model, and this is where experimental values lie abroad, and we can get there if we parameterize our model correctly. Now the thing is, I made this model, but if you now ask me, is this model correct? Or what would the physical origin be of any ions being attracted to the surface? All I can tell you is, I don't know. This model fits the data, but is it right or not? This is what we have to decide based on really atomistic insights, and that is why the atomistic insight, I think, is important if we try to do reliable modeling. Now, this being said, I also want to highlight 2 very recent publications that connect to this. One is by Niels Bruch, who has made a wonderful model in which he can take electron-ion correlations into account through a Feynman-type approximation, where he takes certain Feynman diagrams of this correlation into account, leading to the fact that he can include image charge interactions in the mean field type models, which I think is a very beautiful model. And indeed, when he uses this model and makes the image charge interaction large enough by bringing the image charge plane close enough to the ions, again, he can reproduce the experimental data. But there's also another recent publication where they show that they can also get similar effects by just taking water orientation into account. I haven't gone all the way through this paper yet, so I can't tell you much about it, but I think it's an intriguing thought, and if that's true, I think that would actually be quite beautiful. But anyway, what we need, I think, is this atomistic insight to really know what our models do and how we should build them. And what I want to focus on in this talk is a bit on the atomistic structure that the ions actually form at the interface. And the reason that I want to focus on this is twofold. Once, there's a lot of literature that experimentally we see these ions to have a large impact on our reactions. So it's interesting from an experimental perspective. I think in connection with this workshop, the behavior of the ions is interesting because this part of this workshop will focus on also implicit models, and there knowing more about what our ions do could improve these models. So that is why I chose to focus on this topic. Now, fortunately, also for the behavior of ions, we do have insight from experiment. So what I'm showing here is data by Mariano Monteiro, who measured X-ray crystal truncation rods. And from this, when you build a model, you can extract the distance of, in this case, cesium atoms from a hexagonally reconstructed gold surface. And you can see that this distance of the ions depends on the potential. In fact, it depends on an absolute potential. The silver chloride scale is similarly to the SHE scale, so it's not dependent on the pH. So they come closer, but in particular also they become actually very close. So this is then found around 3.8 angstroms from the surface. And that's interesting insofar as if we now picture such an interface, this is approximately 3.8 angstroms out of the surface. I draw a radius around here, which would be the radius of the first solvation shell of cesium. It doesn't fit. So the ions sit closer to the interface than what you would predict if you just take an ion, including its solvation sphere, and try to push it to the surface. And I think this is relevant. And it tells us that whenever we try to build a mean field model, an ion in the bulk should be different from an ion at the surface, where clearly something happens with this solvation shell. We can also visualize this here. This is a snapshot from an ab initio molecular dynamics simulation. And I just highlighted 3 of these ions here that are somewhere around these experimental values. Now, clearly, they'll not constantly stay there. And in fact, the time scales of these are probably too short to correctly predict where they exactly sit. But at least these 3 ions here sit where we expect them experimentally. And you can see that none of them has a water molecule below it. So that looks as if these ions desolvate, right? But let's ask a bit more details about the exact psychology of these ions and really look at their solvation spheres. So I can track, in every snapshot, I can look at my ions and decide, okay, how far are they from the interface, and I can bunch them together depending on distance. And I can look at their solvation shell. And this is the angle distribution of all the angles to all the water molecules around one of these ions. Now, if you are completely disordered, you expect this to be a nice cosine function. Why is this not working? Here. Like this, right? So as my ions are far away from the surface, in this case more than 6.2 angstroms from the surface, we find a distribution that is noisy, but it's more or less a cosine function. Now this is further away from the surface than what experiment predicts. So let's bring our ions closer to the surface. And now you start seeing things happening. Suddenly, these low angles here, which would be a water molecule sitting directly below the ion, become forbidden. But this in itself does not say that we already lose solvation. This in itself only says that we are trying to orient our solvation shell such that we can get the best possible opening angle. So I'm drawing this here for a octahedral coordination because that's all I can draw. And you can essentially see that once we put the tetrahedra down, we can get a certain opening angle. Now, you can do the exercise. Cesium has a higher coordination number than this, somewhere between 8 and 10. And the funny thing is, you can look up how to try to distribute 10 particles around a sphere. And now, I'm not a mathematician, but apparently this is not uniquely possible. You cannot equivalently distribute those. Now, nice mathematicians have found models that approximate this for you. So I use these models. And using those models, you can find that the opening angle that you can get by orienting something with these coordination numbers optimally would lead to an opening angle of 55 degrees. So anything that has an opening angle less than 55 degrees is just about fine. It's just an orientation of my solvation shell. So we go closer. And now already we see that for distances between 4 and 5 angstroms from the surface, which are distances that are found in experiment at potentials closer to the potential of zero charge, we actually get already opening angles larger than that. Now, from my simulations, I think that this is still not a desolvation. This is just a distortion of my solvation shell. How do I know? Because I can track these, the cumulative distribution function as a function of, so I can track this, and I'll just still see that I have essentially not desolvated anything. Essentially here, these are the different distances of the ions from the surface, the different colors, and it's not desolvated yet. At least that's what it seems. And I can also track the angles between the oxygens of my water, and I see that there suddenly the angle distribution changes. So something happens with my solvation shell. I go further, and now is the point where also in my simulations I do see a slight desolvation of approximately 10%. So this is not a lot, and it really only happens at these lowest distances, which we did find in experiment when we go to very low potentials. So what does that tell us? It tells us that the solvation shell is not a sphere, and we should probably not treat it as such. It also tells us that cesium can partially desolvate. Okay, so let's ask again about the psychology of our ions. Why do they partially desolvate? And we can do a back of the envelope calculation as we bring our ions closer to the surface. They will get lower in the electrostatic energy will be lowered, while we have to pay a cost because we start to desolvate them. So we take the solvation energy, take a tenth of that. That's approximately 270 millielectron volts for cesium, and we can approximate what the gain in electrostatic energy would be, and the two values fit. So it makes sense that cesium would like to desolvate. Now the funny thing is we can do a few more ab initio molecular dynamic simulations, and we see not only cesium desolvating as it comes closer to the surface, we also see the same for potassium, sodium, and lithium. So what I'm plotting here is the coordination number as a function of distance from the surface, and the thickness of the line represents how often we found this particular distance in our ab initio molecular dynamic simulations. I'm not saying that these distances are converged in any way, but whatever you see is probably possible, because otherwise we'd probably not have seen it. And you can see that all these lines go down as we come closer to the interface. Sodium, for sure, goes from 6 coordinated to 5, and maybe even to 4. And even lithium seems to desolvate from 4 coordinated to 3 coordinated as it comes close enough to the interface. We only see this happening at high enough potentials, though, or low enough potentials, I should say. And this is now strange insofar as if we think about the solvation energy of lithium, that's approximately twice the solvation energy of cesium. And while for cesium, I can take out approximately a tenth of its solvation shell because it has enough waters, for lithium, all I can do is to take out a quarter. So the energetic cost for desolvating such a lithium by 1 water molecule should be approximately 4 times as high as what we had for cesium. Now multiply this number by 4, and this doesn't work out anymore. Now, I guess the reason is that lithium is actually, with 3 water molecules, not quite as unhappy as we would believe by just taking 1 quarter. But it's interesting to see this actually really happening. And this desolvation of the ions at the surface also has a fun effect on where we end up finding the ions with relation to the surface. Now remember, these are AIMD simulations. We simulate for 20 picoseconds. Probably we are not converged. I did a trick here. These are simulations with 4 ions, and what I'm plotting is the location of the closest ion to the surface. And that seems to be more stable than if I were plotting the average. And what you can see is that sodium seems to be closest to the interface. We see that at low potentials, or at potentials closer to zero. We see this or closer to the potential of zero charge, I should say. We see this at potentials more negative from the potential of zero charge. We see this with hydrogen coverage on the surface. We see this without hydrogen coverage on the surface. This seems to be stable. And it's strange insofar as we now have an ordering of these ions that neither follows the ion size, nor does it follow the hydrated ion size, which would be exactly the opposite of the ion size. So lithium would be biggest, and cesium would be smallest. So that's kind of strange. And we can say, OK, fine, this looks stable, but it's still AMD, so let's do better. And we can try to do machine learning and extend our timescales. And I'm saying this because we are trying to embrace stochasticity. And I think what we are seeing here is something rather stochastic. What we did is we prepared a training set with 1 to 4 ions on our surface of, I think it was a 4x4 surface. I'm not 100% sure. I'd have to ask my student. But it also doesn't matter. We took that. We split that into training and tests. And we built models either using GRACE or DeepMD. And then we said, OK, now let's predict where we find our ions. So this is the histogram of the ion density. And GRACE predicts a considerably different profile than DeepMD. And if we take these profiles and invert them such that we get free energy differences, and the changes in free energy difference is 20 MeVs, which is considerably bigger than the RMSE in the training set, which is about 1 MeV per atom. So something doesn't work out here. OK, fine. You should never look only at these RMSEs. We know that. We've learned that. So let's do better. Let's take our entire data set. We split that up in different manners. And we train 3 different models completely from scratch and let them predict this again. And the shaded areas that you can see in some of these cases are the differences between these 3 models. So these 3 models still predict the same thing. Now, we are so far not entirely sure yet whether this is just a question of these models being overconfident and us really having to include more training data, which I think would be very hard to know just looking at this, or whether this is really still an issue of the models. We think that maybe part of the problem is that we trained on 1 to 4 ions. We thought initially that this should not be an issue because our cutoff radii are essentially big enough to see the entire environment. But maybe it still doesn't like that. But this is ongoing work. I just thought it's fun to see. So I decided to show this. There was a question here.
Sorry, what was the DP?
The DP is DeepMD. DeepMD.
OK. And other machine learning models.
It's another machine learning model, yeah.
Katharina, so none of these machine learning models are charges in there, or?
So those are just the regular charge-blind models. And of course, they'll break down when you kind of pull your ions far away from the surface. But essentially, for all what we trained here, basically all the data that we have, the ions are within the cutoff. So you would think that as long as they're in the cutoff, it should be possible to learn the electrostatic interactions on top of everything else. But now, yeah, we, as I say, I'm not quite sure yet what's happening there. But for sure, we could try to do better by learning charges with it and trying to improve that.
I was only thinking if it's getting really very close, whether you have already said some kind of depolarization so that the charge state changes.
But that, in principle, if you depolarize, in principle, you should be able to learn that with a regular machine learning model, right? So as long as
a distance, so not if it is globally electrostatic, so you don't really see your full capacitance then. So
but the ions, the distance of the ions from the surface is so short that the ions see the surface and the surface sees the ions, right?
Yeah, but only one, so the other one, so...
I think they should, in principle here, basically for all the data, all ions should be visible to the surface. So they are all quite close to the surface. Just think of this other snapshot, the ions they don't really like to be far away. So anyway, that was a bit of a detour, sorry. So I'm coming back to what we had, which was our sodiums coming closer to the interface than anything else. So let's believe that for a moment. I think it's real. And let's ask again about the psychology of our ions. Why on earth does this sodium behave strangely? And the nice thing is that we get this behavior also when we use force fields. So I use force field. Sodium, again, is closest to the interface. Now, you can say anything about force field, but the very nice thing is that I can play with the parameters. So what we did is we took this lithium here, and we changed the parameters for the lithium metal interactions to be those of the cesium metal interactions. And what happens is the following. Essentially, we have no change. The lithium still sits where it sat before. The only thing that changes is that the slight pre-peak that we had here, which is invisible on this scale, is gone now because this is within the exclusion region of the cesiums. Now, what does this tell us? This tells us that the positions of the ions are dominated very strongly by the water, because that is all the interactions that we are left with, and not so much by the interactions with the metal. So let's take this idea further, and maybe what I said you can see a bit more easily here. In blue, you can see the water structure, and what I'm plotting here is lithium, sodium, and cesium at different surface charges, so colors as higher surface charges. And this is the concentration of the ions. And in blue in the background, I'm plotting the water concentration at the highest ion charge. So you can see that the water concentration is slightly dependent on the ion type once we have many ions at the interface. But what always remains the case is that you have a very strong layering. In fact, it's stronger in force field MD than it is in AIMD. So we are probably over-structuring whatever we are seeing. And what you see is that all these ions, they have preferential positions that slightly depend on the surface charge, but these preferential positions depend on the ion type. So they're not all the same. And to understand that, we have to go back to the properties of our ions. And now again, all our ions, they like particular solvation shells. And lithium likes this tetragonal solvation shell, while sodium likes this octahedral thing. And now if we take these ions and try to move them through this layered water, we can find situations in which the water molecules will align well, now for example, with these water layers that are there already. So here again, these two sit in the lower layer. This one sits up there. We can do the same exercise for the sodium. We bring it closer and turn the solvation shell such that it fit. We just had one situation where we had two waters up here and two down here. But we can also start to turn it like this. This is only possible if we desolvate this one guy here. But then we have 4 water molecules sitting in this plane of waters where we expect a high density, where probably water molecules feel at home. So this should somehow be a favorable structure. And we can do this exercise, and it doesn't work out one-to-one, but it's very close. This is why I put dashes here. If we just look, how can we put our ions in between these water layers, and where would the ions sit once we have found a configuration that seems favorable? This corresponds very nicely to the peaks that we see in our force field MD. So essentially what we learn from here is that it's the water layering that imposes the layering of the ions. Or as my PhD student formulated it, if it fits, it sits. So we now kind of understand why this sodium likes to sit close to the interface. What does this tell us? Very often you see in literature an argument of why different ions have certain effects based on the fact that the different ions will lead to different electric fields because the different ions sit at different positions, leading to a different capacitance and hence a different surface electric field. And they always argued that the order in the capacitances should be according to the hydrated ion size. Now, oops. If this is the distance of the ions and this has nothing to do with our hydrated ion size, how does this argument work? And we actually tried. We took this data and computed the capacitance. And I'm plotting the capacitance over the average ion platinum surface distance, so the distance of the ion to the platinum. And what we would expect is something that goes up in some way. Now, this is with water at the interface. This is without water at the interface. Yes, maybe we get an upward trend here, but what does then sodium do down here? Could be inaccuracies in our simulations because we have error bars. But I think what is very telling is this incredible decrease in capacitance here when we add hydrogen, which does not correlate with a strong change in the position of the ions from the surface. There's a minuscule change in the position of the first water layer, about 0.1 angstroms. And the ions maybe follow this 0.1 angstrom difference, but for sure there's no big difference that could explain this. So there's something else going on here. And this something else, I think, must have to do with how the potential profile at the interface looks like. So if we have really the interface and then our potential rises until it has met kind of this counter ion plane to stabilize, then really we should have at large ion surface distances, we should end up with a small capacitance, and at small ion surface distances, we should end up with a large capacitance. Now, if otherwise we have somehow here a different dielectric response than further away, we might actually have most of the rise or most of the potential drop in this innermost layer, in which case the capacitance is barely influenced by where the ion sits. And I think that we have this. I think that nearly certainly we have this in the case where you have hydrogens absorbed, because otherwise I cannot explain this decrease in capacitance. Now, we got intrigued by that, so we also tried to look at the dielectric response of the water, and we took an idealized surface. We just have a bare platinum surface, and we stuck at PZZ, because obviously, so the potential of zero charge, because this should be potential dependent. So we had to make a choice, and that is the choice that we made. And if you think of the response of water, we have three contributions. One is the orientational contribution of the water. One is an ionic contribution in which the water can do that to kind of accommodate or to counteract an electric field. And the last one is the electronic response. And if you look into literature, most of the work focuses on this orientational response, probably because this is done with force field molecular dynamics, which doesn't account for the electronic response. You might have seen these plots. You get these weird oscillatory dielectric response, which is interpreted in the way that you probably have to average over a larger range, because otherwise you would get a negative dielectric constant. Now that's nice, but the problem is that we are actually interested in this part here, and there's no water there. So there's no water that can orient. So clearly what we really need is the electronic response. And there have been efforts to try to take this electronic response into account, and there are very nice papers. One of them here by Jiaxin Zhu, a PhD student whom I co-supervised with Zheng Chen, and another one here by Dijsselbeck. So this one uses machine-learned molecular dynamics, but includes Wannier centroids to account for the electrons in the water, and this one uses AIMD. But both of them cannot correctly account for the metallicity of the electrode. So you'll see the dielectric constant going to 1 inside the electrode. And this is something I wanted to avoid. So what we did is we started with a machine learning model. Why? I guess because we can, and B, because we wanted to be sure that our water here is really equilibrated. We did 500,000 of tests on whether we believe our machine learned potential. I think I believe it. And then from there, we wanted to get the dielectric constant. Now, these machine learning models, again, they were blind to charge, so we have to go back to a DFT description. So we took snapshots from these AIMDs. In fact, these were periodic systems with metal, water, metal. So we had to introduce also a vacuum interface. So we just cut part of this out. And then we can apply an electric field. And we compare the charges without electric field or with increasing electric field, which gives us a change in charge density. And from the change in charge density together with the electric field that we can measure here in the vacuum, we can extract an electronic dielectric constant. So this is purely electronic because for each of those snapshots, we have frozen the atoms. So this is only electronic response. Now, first, I would like to focus on this here a bit. I think it's fun to see such a snapshot, how this looks like. So this is really the change in density in 3D space. These are my platinum atoms. And you can see that they polarize kind of outside here in something that looks a bit like a p orbital, maybe. And the water molecules polarize with more positive charge density. More negative charge density and more positive charge density. We also have here the situation of one water molecule being bound to the metal surface. You see a funny thing here. This metal still polarizes, but it polarizes below, I guess because this orbital is involved in this bonding, so cannot polarize that nicely anymore. And then we see the water molecule on top. You'll also see in this profile a funny thing because we have a negative peak here, which is this charging of the water. But you'll also see a negative peak down here, which is charging of the water, maybe, or not. I think that Nico will talk a bit more about this. But thing is, I think quantum mechanically, we cannot distinguish whether this is a charge transfer into the water or whether this is a decreasing polarizability as we go further away from the surface, which would both have as an effect that we see a negative spike here. And because I cannot tell whose electrons are whose, I cannot say whether this is a polarization or whether this is a charge transfer. I also personally don't care for this particular problem. All I wanted to have is the dielectric constant, or otherwise the inverse dielectric constant, which is what directly drops out. So what you see now here is that the dielectric constant, the inverse dielectric constant in the metal is close to 0, as we'd expect. So the dielectric constant is infinity. Then we see this weird negative spike. This is not noise, I think. This is a change in the spilling of the electrons as you apply an electric field to the electrode. And then you see a sharp downfall, and finally you'll stabilize at something that is actually close to the optical dielectric constant of water as we would expect. Now let's zoom into this interface a bit more. This is this downfall here. And the downfall very closely resembles what we'd have at the metal vacuum interface. So approximately 1 angstrom out of our metal, my metal stops being metallic and the dielectric constant drops very rapidly. And then you get these oscillations. And if you look at these oscillations and you simultaneously look at the electron density that the water has at this interface because of the water layering, they look very similar. So we can actually build a very simplistic model in which we say the dielectric constant is a sum of the metallic response and the water response, just that the water response we scale by the electron density. And out comes the orange line. which is already very close to our blue line that we measured. There's a small difference here, which I think is probably due to the interaction of the waters with the metal. So what we see is actually if we compute the Wannier orbitals of a water molecule in vacuum on the water molecule at the surface, then the Wannier orbitals at the surface become elongated, and typically an elongated Wannier orbital is related to a higher polarizability. So that would make sense that this increases the polarizability here a bit. Now again, here the water orientation will not have kicked in yet we have a relatively low dielectric constant of around 2. So it seems reasonable to assume that we really have this kind of gap in which we have a low dielectric constant. So again, I think that this is a realistic picture to have in mind. Now, another thing that is often discussed is whether ions cluster at the interface. So it's not only how close do they come, but also do they, for example, form 2 or more layers as you have more and more ions at the surface. So to look at that, I'd like to come back to our force field molecular dynamics simulations that you have already seen. And what we did here, the surface charges that we go up to at maximum are quite reasonably high. They're probably high enough to bring you approximately 1 volt away from the potential of zero charge. And what you see is that for cesium and sodium, this is a logarithmic scale. So there's essentially only 1 layer here of ions that we have. Only for lithium, we happen to have 2 peaks that seem similar. But I think that this may not be a question of this fitting, but just that these are kind of energetically similar. So they like to be in both. But it does not seem to be necessary to actually put ions into several layers, at least not under these surface charging conditions. And we can ask the question why. And to do so, I'd like you to look at these snapshots of my ions at the interface. So this is lithium, sodium, and cesium. And what you will immediately see is that all of them at the interface can share their solvation shell. So they come very close to each other. And before you tell me I'm crazy and this is an artifact of the force fields, at least for sodium and for cesium, the structures that we find have been either seen for interfaces with ice water on top of metal surfaces, or have been predicted by very high-level theories in the bulk to exist. And since at the interface, you should actually get a dipole-dipole interaction rather than a charge-charge interaction, having these very close contacts of 2 ions should get energetically more easily accessible. So it makes sense that this happens. So you really see these ions bunching and sharing their solvation shell. There's also some imprint, by the way, from the metal through the water structuring, but that might be a force field artifact, so I'm a bit careful there. So okay, fine. At 1 volts versus the potential of zero charge, I think ions don't need to form 2 layers. But in this statement, there's already an important point. I said 1 volt compared to the potential of zero charge. So important is this potential of zero charge. And I want to say a few words about this because it ends up being very confusing from time to time. So the easy system is when you have no adsorption processes on the surface. Then the concept of potential of zero charge is very simple. Whenever there's no charge on the surface and no excess of ionic charges in the double layer, this is your potential of zero charge. Now it gets more complicated if you include adsorption processes. So imagine we have an OH minus in solution that might want to adsorb here to form an OH, in which case you'll find a current flow, and we measure this as a pseudocapacitance. But in this situation still, there has been a current flow, but this surface is not charged here, and there's no excess of ionic charges. This is what we call the potential of zero free charge, PZFC. And we distinguish that from the so-called potential of zero total charge, which would try to compensate this outflow of electrons by an inflow of electrons. Now, if you now put electrons in here again, they won't go on the chloride, because that's not where they want to sit. Instead, they'll kind of go onto the surface, charging the surface, and you'll have to make sure that you get excess charges in the double layer. Otherwise, this does not work. So these are two potentials of zero charge. I'm saying this because it leads to confusion. And you might say, well, this is my private terminology. And maybe, indeed, people have used terminology differently. But I think it's important that we actually try to stick to one terminology, because these different PZCs are also related to different observables in experiment. So the PZFC is where you expect this minimum incapacitance that we saw on the very first slides, while the PZTC is where you measure the electrocapillary maximum. And the problem with this is that very often you find either incorrect explanations of this or maybe misleading, or actually missing. So maybe a nice example is that Bard and Faulkner, which is the Bible of electrochemistry. They don't distinguish different PZCs. They just say PZC, and then you're left for your own to guess which one they are talking about. So we have seen yesterday this paper about potentially confusing potentials in electrochemistry. So I think this is, again, an example of a potentially confusing potential. The potential of zero charge is potentially confusing. And I want to highlight a few facts. First of all, this potential of zero free charge, in principle, I can define a potential of zero free charge for every surface. I can define this for the bare surface. I can define this for a surface with one adsorbate on it, two adsorbates on it, and so on. Each of those will have a different potential of zero free charge. Not all of these potential of zero free charge will actually occur in realistic scenarios, because maybe this potential of zero free charge is at the potential where the hydrogen doesn't happen to be adsorbed. So then you can't measure it. But we can still have this concept of it, and it might help to explain why we have how many ions near the surface. The second thing is that this potential of zero free charge, I think we should expect to be more or less independent of pH, because imagine I add now here KOH into my solution. This will probably not affect much the interface dipole here. It will probably also not affect much the dipole of the waters here, and that is what defines the potential of zero free charge. So probably there's a weak dependence on the pH, so my PZFC should be fixed on an SHE scale. The other thing is that we should not confuse this PZFC with the potential at which a certain adsorbate adsorbs. So imagine you did this simulation here, you put a hydrogen here, I measure a potential. This potential is the potential of zero free charge. It is not the potential at which I will reach this hydrogen coverage. And I want to give a very simple explanation of why this is impossible that this would be, and that is if I'm plotting the hydrogen coverage as a function of potential versus SHE, then depending on the pH, this coverage will increase at different potentials. While this potential of zero free charge that I'm measuring here is independent of potential, so it's just fixed here. So it does not tell me where you start adsorbing hydrogen. I've seen this in literature. This is why I'm trying to highlight this. So this is, again, it's the PZFC at the given surface coverage, but it has nothing to do with where I have adsorption. What this also tells me is that at a given surface coverage, depending on the pH, So let's say I have this surface coverage. I will have a different distance from the PZFC. So I'll have different electric fields. This has been often used to explain pH effects in electrochemistry. And the same holds true, in fact, for any reaction that involves proton-coupled electron transfers. And I want to give as an example HER. Again, we have that this depends on the pH, while the PZFC is pot. So if I'm looking at this current here, this will occur at different field strengths. Now maybe to go a bit further, also a comment, we have discussed these reaction profiles that you can get from free energy sampling. And very often you see such a plot in a paper. Now such a plot alone is actually rather worthless because what you need is an information at which potential versus SHE this was actually measured, right? So without this information, this plot is useless because as I change my potential, this will start changing. So if you plot such a thing, give this information. The other thing that is strange here is that somehow we've lost the pH dependence, right? I'm at a certain potential versus SHE, let's say this one here. Depending on the pH, you should have a higher or lower current, right? This should not react at all yet. But out of free energy sampling, I'll always get one curve. So where has the pH gone? And the answer to this is that what we are plotting here is a G0. There's no concentration terms included yet here. So if you now take this barrier and stuff it into a kinetic modeling and you correctly account for the attempt frequency, things come out correct again. Now, confusingly enough, some people plot G0 in literature, and some people plot G and change this depending on the pH. Some people do these corrections only for specific species, so we are left with a mess. And I think we should be aware of that and try to avoid making this mess. So take-home messages, indicate the potential, and clarify exactly what your energy means. Is this G0? Is this G? Which corrections have been applied? Now, we still haven't answered the question yet of our PZZ, and I can see that I'm being interrupted. Maybe just a very brief word. If you look at this, and this is a compilation of literature results that Arthur Hagopian, a postdoc that I share with Mark Koper, has done, it looks as if we had something that is potentially stochastic. So these PZZ values differ wildly. You give me a value that you want to have for the PZZ, I pick a literature for you that gives you this value. So what is happening here? Why is determining the PZZ so hard? And usually these PZZs are determined from AMD simulations. And for sure we have fluctuations in there, and maybe the time scales are too short. But there are other effects that also play a role, and that is that usually we only take the gamma point into account, and you can see that this very, very strongly influences the work function. So even if you take a 6x6 cell, this can still be easily off by 200 MeVs from a converged situation. Then we also have that very often these calculations are done in CP2K, but the work function that you get from these Gaussian plane waves are different from the work functions that you would get using plane waves. Additionally, if you look at how well work functions are actually predicted in DFT, very often people say, that works very well, but very well is relative. In electrochemistry, very often we care about 50 MeVs, and you can see that we are structurally off by at least 200 MeVs. And this can go terribly bad in some cases. Now, nicely enough, all these effects are something we can account for because in principle, we expect a linear relation between the work function of the PZZ, so we could add correction terms to our calculations. This is often not done. I think it should be done. But another thing is how we compute how we actually compute them. And now there are different methods. I don't have the time to go into it. There's the computational standard hydrogen electrode method, in which you take the bulk potential and then correct with values. There's some uncertainty related to that here. We can take a work function approach in which we have a vacuum interface. Maybe just one thing to highlight here. In literature, there have been 3 kind of versions of this this vacuum approach or work function approach. One in which a dipole correction is applied, in which you can get a plateau region here, and you can compare that to the Fermi energy, giving you the PZZ. I think this is the most accurate. Some people have said, oh, well, we don't care. We just take the potential that we have in this region here, and it's close enough to what we should have. That's true, but it can lead to errors of, at least we have seen, 0.1 EVs. And then finally, people have said, oh, we just put a polarizable continuum here that gives us a flat value here, and we take the difference between this flat value here and the Fermi energy. Now, this is incorrect. And it has to be incorrect because if you look at this here, here we have a metal vacuum interface. Here we have a metal solvent interface. They should have a different work function or PZZ, while this here gives you one plateau region, and in the calculation you also have one Fermi level. So now you end up with having work function equals to PZFC, which is impossible. And the reason is that you just have charging here. So this is nonsense. That doesn't work. Now we can try to explain differences here. We used the same trajectories and evaluated with the CSHE method and with the work function method. You can see this still varies a lot. We can improve on that by accounting for the water vacuum interface, makes life a bit better. This I will skip anyway. But what I cannot skip is to thank my group. So just let me get to my group. There we are. So these are the people who actually did the work. So they are the most important ones. And with that, I'd like to thank you also for your attention. There's a brief summary here. And I should also not forget my collaborators.